Okay, let's start. This is RC4 encryption algorithm. This is a broad algorithm that you may see. This is the algorithm. If you have 256 bytes array in S, some vector or an array, 256, for example, 256 characters, 256 number, then we can use modulo function, which is a mod 256, by increasing variable I and j, right? And I and j will be modified at each loop. So this loop continues. Yeah, it's not just infinitive loops, but as far as there is I and j's, and there's something that you can swap, but you can run this as much as you can. And also this is this encryption for streaming data, which means the data can come continually. So for each data item, this can generate the key. So for one data, one key to be generated, and then they can do exclusive OR operators applied. Therefore, encryption will be, cipher will be generated, and cipher will be shipped out through the wireless communication. So this is the output, but at each the modification I and j, you can swap the same vector s. Okay. This algorithm is very simple, but total number of possible state is 256 factorial, which is almost 2 to the power 1700. If you have a calculator, you can I can find out 2 to the power 1700. How big is it? The bigger number indicates that it's almost impossible to guess, right? Impossible to identify. So I have a calculator here for scientific. So no, not in this way. So 700. My iPhone calculator cannot calculate 2 to the power 700. So if you calculate, for example, 2 to the power 700, not 1700, see how we cannot do that. So that is a very big number, 2 to the power 100, for example. Then that is power 30. If we have 2 to the power 100, which will be, I think, 1.5 times 10 to the power 30. 10 to the power 19 or something like that, then it is called Google, right? Google, similar to Google. 10 to the power 19. There's no word that you can call 10 to the power 30. But this is a lot smaller than, lot smaller than, wait a minute, a lot smaller than, lot smaller than 2 to the power 1700. What is the implication? So almost impossible to guess, because this can generate that many different states, possible states. Okay. So this is a very, very good algorithm, but RC4 has been cracked many, many years ago, right? But since that time, they modified and reinvented. To run that algorithm, initialization vector is needed. That is this. So we need to generate initial permutation from a key K. So this is a given, right? This is a very simple key that can be given. So those key can be shared between your station, your laptop, and access points very, very easily. The maximum length is 2000 bits. So K can be used to generate the initial vector. The algorithm is a for loop again. So two for loops are running. So this is the basic algorithm. So last time we started to apply that, right? Instead of using 256 bytes, we're going to use only one byte, 8 bits, right? 8 bits means, yeah, 8 bits. So, and also given key is 1236, okay, 1236, because we use only 8 bits, and given key is 4 bits, so we repeat the 4 bits to fill 8-bit long spaces. And then state vector is just numbering, just enumerate from 0 to whatever the number. So we start from this, okay? So first we apply the algorithm to prepare. Once you prepare this, then later we apply the real algorithm to generate the key. This is the key that we want to use. Once you have a key, that can be the first key to apply the first the data in the data stream. So second data, we will use the second key, and third data, third key. So every time we have data streams, we have different key generated. Therefore, no one can figure that out. In theory, key that has been used, say 1 minute ago, is not the same as the key that we currently generate. So every time it generates new key. So that is the beauty of this RC4. So we applied here. So let me help you. One more time. Okay, this is given state vector. This is the key. We call that temporary vector, T. So finally, whatever that we have, this state vector will be used to generate the key. So S starts from 0 of J, and I is increasing. So I start from 0 to 7 only, because we have 8-bit mechanism here. So for I equals 0, which is the first step here, J will be modified. J will be J plus S of I, because we have I here. So initially that is S of 0. So this will be S of 0. S of 0 plus here T of I, which means T of 0. S of 0 means 0. T of 0 means 1 here, right? All the number in this vector space on array can be accessed by index. Index counts from 0 to whatever the number, right? So this is the index. So fifth element of state vector S contains, which is 4, and this is 6th, this is 7th, this is 8th. So add them up, which is 1. 1 mod 8 equals 1. So I is still 0, but J is reset to 1. So that is done here. Then we swap Si and Sj, which means we swap Si means S0 and Sj means 1. We want to swap this. So S0 is this, S1 is that. So we swap these two, 1 and 0 only. So that is this. So this is a new state vector. Okay. So we're done for the case of I equals 1. And then we will do I equals 0, done. And now we will take a look at the case of I equals 1. So for I equals 1, then J equals J plus. J is initially 1, so this is nothing but that. And then S1, Si, which means S1, because that is that. And then Ti, which is T1. T1 is, T remains the same. This is all the time, remains the same. S keep changing. So they are, so T of 1, which is this, right? So number 2 comes here. S of 1. Now we need to look at the new S. Right? S of 1 is this. So there is a 0. So with them, we add them and divide by 8, and remainder is 3. Okay. So I equals 1 and j equals 3. I equals 1 and j equals 3. Then we need to do swap. Swap I equals 1. S1 and S3 will be swapped. S1 and S3 will be swapped. So S1 is this, S3 is this. So they will be swapped. Therefore, we will have a new S. So these are swapped, therefore 1, 3, 2, 0. So 1, 3, 2, 0, and that. So we done the case I equals 1. Now we need to increase I by 1, so which is I equals 2. So we apply that here. So J equals J, current J is 3, plus SI, so S2, plus T I equals 2, which is nothing but 3 plus S of 2 is 0, 1, 2. S of 2 is 2. T of 2, 0, 1, 2. That's a 3. Which is 8. 8 divided by 8, which is, remainder is 0. So what do we need to swap? We need to swap, what is S? What is S1? SI. SI is 2. So S of 2 and S of J. J equals now 0. So we need to swap them. S of 2 and S of 0. So from here, this is a 0, 1, 2, 0, index 0 and 1, 0 and 2 will be swapped. So 2 comes first, 2, 3, and instead of 2, we will have 1, and the remaining the same. Only these two are swapped. Right? And after that, which is 2, 3, 1, 4, 5, 6, 7. 2, 3, 1, 0. So 2, 3, 1, 0. So S is 2, 3, 1, 0, 4, 5, 6, 7. So we increase I, which is I equals 3. I equals 3. So currently, right now, J equals 0. So J equals 0. So new J will be calculated by current J, which is 0. And then S of I is now number 3 here. So 3 plus T of 3. So S of 3 is 0, 1, 2, 3. There is a 0. T sub 3 is 0, 1, 2, 3, number 6. So this is a 6. Which is a 6? 6 modulo 8. Then modulo is, the remainder is a 6. So that is a 6. So finally we need to swap. S of Si and Sj. Si is a 3, so S is 3. And S6 will be swapped. 3 and 6 is swapped. 0, 1, 2, 3. So this 4, 5, 6, 6, they are swapped. So 6 comes here. So 2, 3, 1, 6, 4, 5. So they are things swapped. So my explanation here is my practice. And if I do more explanation here, then it helps me to avoid all possible minor errors, right? So I want you to do that also, so that you can avoid all possible errors, especially for your midterm exam, right? So I want you to do fifth step, which is I equals 4. And then we will come back to do it together. So one step only at this time. So I'll give you 10 minutes, okay? That's the same way that we did. Anybody done? So what is S? What is your S? 2, 3, 4, 6, 1, 5, 0, 7. Anyone has different state vector generated? Anyone has different? Everyone's the same? Or you do not know yet? Never tried? Okay, let's do it together. So J equals, what is the current to J? 6. So 6 plus, and then SI is 4 plus T sub 4. I3 we done already. One more time? Then how come everybody is the same? Okay, Olivia, what is yours? 2, 3, 1, 0, 4, 5, 6, 7. Anybody has any? 6? Okay. So as Pamela said, this is not right? Because she used the different eyes. So Olivia, you may be the winner. Me neither. So help me to get your answer. Okay, what is yours? 6, 5, 1, 0, 7. 2, 3, 1, 6, 5, 4, 0, 7. Okay. We'll see. Anybody has any? Okay. So SO4 is, oh yeah, it's 0, 1, 2, 3, 4. SO4 is 4. TSO4 is, go back here, 0, 1, 2, 3, 4. There's number 1. So that is number 1. Okay, which is 11, right? So 11 mod 8. Then what is the remainder? 9, 10, 11. 3? Yes or no? 3. J equals 3. So we need to swap. Swap S of 4 and S of 3. So from here, so 0, 1, 2, 3, this and that. Then 2, 3, 1, 4, 6, 5 was 4, 2, 3, 1, 4. So 2, 3, 1, 4, 6, 5 or 7. This is new or similar to someone? Or exactly the same as yours? Anybody have this? Raise hand. This. Jay? Jay, come here. This is the. Any miss? Did I miss any? J, first J is 6. That is this. That is the initial J. And then S of I is from that iteration. So 4 and 4. So S of 4 from here, 0, 1, 2, 3, 4. There's a 4. And T sub 4 is from the previous slide, which is 1. So that is 11. And remainder is 3. So we need to swap 3 and 4, which means 4th and 5th. So 0, 1, 2, 3, and 4. So 4 and 6 will be swapped. So this is it. Anybody has this? This? Correct. The very previous. Okay, do one more time. For the case of I equals 5. You need to solve at least one, therefore you could do for your midterm. So right now what you need to use, S is this, J is this, I is this. 11 from 6 plus 4 plus 1. This formula, which is this. So 4 is from there initially. 0, 1, 2, 3, 4. This is 4. There's an index, yeah, position number, index. Yeah, previous. Just write previous. This. For this, so for this calculation, you need to use this S, not all the way up. Just one step before. This T never changes. Which one makes you confused? Which one you do not like? Right. If you see this, David, this is the J that we uh, newly created. This J is the J, the previous. Previous J is used to create new J. So although you see they are the J, they are not the same J. This J is the use that you have a current J here. Which one? Whatever you compute within this parenthesis, if that is 11, then modulo 8, which means you divide it by 8, and then what we want is the remainder only. There's a modulo function. So 11 divided by 8, then can be divided by 1, and the remainder is 3, right? Which one? There's a remainder. 11 divided by 8. What? Oh, there's a new J? Oh, new J. We didn't do. Yeah, we'll get to that. I didn't do that yet. Hi, Stuart. Oh yeah, of course. But you have to understand the algorithm first. You got it? So what is your answer for this? I equals 5. Which has
Understand the top part, and then you do 10, 5, and 8. I just don't understand how you put them in the format.
then you need to swap. What is
Oh,
swap?
swap
Here,
two
look at the algorithm. Swap. Once you have I and J, then you need to swap
So
I and J.
I will swap
Fifth,
where 5 is, which
yeah,
is right
five
here.
and position
So then
five
this
and
will be
position
5
two.
and this will be 2 when I rewrite it.
No, 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 no. This is the position number. Now we need to count. This is 0, 1, 2, 3, 4, 5. This is a fifth. This is 0, 1, 2. This is one second. So this is the index. These are the index. I and J are index, not the value. Index is this 0, 1, 2, 3, 4, 5, 6, 7. This is index. So I index is 5. So this number, J index 2. So that. So these two numbers, now these two numbers are swapped.
So then this will be 5, 1.
5 and 1, yeah. Oh, now Jessica will. Okay, I equals 5. So every time when you do, you need to go back to the algorithm and this procedure, right? So for I equals 5, now we need to compute J. So to compute J, we need to use the current J. What is the current J? Current J is 3. Thank you so much. Oh, this is not the color that I chose. This. Okay. So number 3, which is came from this, the previous, plus SJ, SI. I is 5. T sub I, that is also 5. Oops, not this. 5. Okay. So that is 3 plus S of 5 is 0, 1, 2, 3, 4, 5. This is S of 5. That is 5. Plus T sub 5. Then we need to go back. 0, 1, 2, 3, 4, 5. This is 5, index 5, the value for the index 5, which is the 6th element, number 2. Number 2 is the value in the sixth slot. So add them all. That is 10. Oh, number 10, that reminds me of Jessica's number. So far, so good, right, Jessica? And then mod 8. See here, mod 8 is always mod 8. Remains the same. This modular denominator number remains the same. Remember that here, that is also mod this. So that is for this, I. Yeah, right. That's a lot longer. This. A lot more iteration. Here we do how many iteration? Only 7 iteration. 8 iteration, mod 8. 125th iteration. To get one S, you need to run so many times. We may do that, then one iteration may take 1 or 2 hours. So you may hate me, or you may kill me. So simplify. Your midterm exam, at worst case, I'll give you 8, but maybe we can practice at 4. No, 8 iteration. Right now we're 8 iteration, but maybe 4 iteration. It's much easier, right? Much easier. Where are we? Okay, here. So what is a modular? Thank you. 2. So once you have this, then swap. Swap SI, which is 5, which is the 6th position, and S of 2, which is 3rd position. 3rd and 6th. So 0, 1, 2, this, 2, 3, 4, 5, this and that, right? Those two are swapped. Therefore, S will be 2, 3, 5 instead of 1, 5, 4, 6, 1, 0, 7. They don't swap, only this and that. 4 and 6 remains the same. Need more exercise or enough? Enough, right? So 2, 3, 5, 4, 6, 1, 7.
We're changing the. Aren't we changing the 3rd position?
Yeah, here. They are swapped. Which is this? Okay, 2, 3, 5, 2, 3, 5, 2, 3, 5, 4. So S equals 2, 3, 5, no 5, 4, 6, 1, and what? 0, 7. 0, 7. And I equals 6. Now you need to compute J. What is the previous J? Previous J is number 2, right? So here, the previous J is number 2. Previous S is this, and previous J is this. Now you can compute for new J and new S. So I'm going to do this silently also. So you could do and see. I'm sorry? Yeah, T remains the same all the time. T is the given key. Yeah, initialized from 0 to whatever the number. If you have 256, then 0 from 255. Initially from 0 to 255, but it is swapped all the time, so that finally you have different S, different sequence of S. But right now you have only 8 numbers, but you have a longer, then you have 256 numbers. So finally, that S will be used to generate the key. We didn't get to that yet. Yeah, yeah. S will be from 0 to 255. So it's a long numbers. David, you want to try? Yeah, yeah. Old J is 2. S of 6 plus T of 6, which is 2 plus 6. 0, 1, 2, 3, 4, 5, 6. Yes, it is a 0. And T of 6 is 0, 1, 2, 3, 4, 5, 6. That is 3.
Mod J equals 5.
If we do mod, then this number only, which is 5.
So we swap
So mod 8 equals 5. Now we need to swap. Swap S of 6 here. Correct. Correct. If you divide the 5 by 8, then remainder is what? Correct. Yeah, 8 times 0 plus 5, that is 5. So 5 is remaining. Yeah. Where are we? So S of 5, S of 6, swap and S of J, which is 5. This S of I and S of J. I is this. What is current I? Current I is 6. J, what is current J? Current J is 5. So 6 and 5 will be swapped. So which one will be swapped? Current S. Current S is this. So yeah, fifth index, index 5 is 0, 1, 2, 3, 4, 5. This is index 5, right? Index 6 is 0, 1, 2, 3, 4, 5, 6. This is index 6. So we swapped these two. All others remain same. Okay? Do you have this? 2, 3, 5, 4, 6, 1, 6, 0, 1, 7. Finally, so I equals 7. Finally, I want everybody got the correct number so that we can, yeah, everyone will have the same number. Same, the very same correct number. Yeah, do it. And I will do it too also this time. Yeah, I will. So there is a 6, the last one. So what is the number? 13, 18? 18 mod 8. Then 2.
I'm trying to code it, and I don't know what's going on.
I cannot do it. No.
Okay, I was just
How can I do
curious
it right now?
if you,
You're very good. Is it C?
yeah.
Great. If what your program produce is not the same as this, then your program's logic is not correct. Yeah.
Did you initialize all your variables? C++ doesn't like variables that are not initialized.
So finally this 7 and 2, which is the last, and this 2 means the third. So 2, 3, 7, 4, 6, 0, 1, 5. Yeah, this is it. Shorten, yeah. Shorten. I do not know. Yeah, shorten step. We'll give you the same number but different key, for example, then you will have different something, right? For example, if I give you different key, then you will have different of this, right? Slightly different. Or if I ask you to do rather than 3 bits but 2 bits, then only from here there. Yeah, if I give you key this and I give you how many bits, then you generate this, and then finally I can give you which one? That I give you. I give you key. S is just serial number from 0 to whatever the bits. If you have 8 bits, then it fills 8 bits. Yeah. And then keys, if I give you, for example, 1, 2, 3 only, then you need to fill 1, 2, 3, 1, 2, 3, and 1, 2. Whatever the repeat, by repeating, you fill. That's what we're going to use for T. Okay. Right. They should be the same size. S and T should be the same size. Correct, yeah. We did that last week. Were you here last week? You missed it, right? We did a lot of mod. Yeah. Yeah, we did that mod. It's very simple. May not be, but is it, as David said, this simply division. Can you divide? Which one? Give me an example. So 10 divided by 8, then can you divide it? Right, the remainder. If you use a calculator, then that's not what we want. No, she's using calculator. That is the reason. Yeah. No. Wow. That is more difficult. I know. So that is more that needs more mathematics. Right. I think you are confusing between the real number and index. There's always the way you can do the programming. Programming can do only index manipulation, not the value itself. Value can be any. Yeah. Whatever currently available will be the value, but can be accessed by index. Index you can increase, decrease. Correct. Yeah. That is a programming. So if you understand this algorithm, then and by knowing a little bit of programming syntax, you can implement it. So probably some of you are already motivated to do some programming, like David and Pamela and many other also. Olivia, throw it to me. Almost.
Is this correct?
You're right.
Oh, my code works.
Yeah.
I was missing an equal sign.
So he did it quick. Very good.
It took a while to code it because
Do you want to practice for full code, 256 code, David? Yeah, I have an example. So what you could do is you can generalize it. Yeah. David, I want you to generalize it. Yeah. For example, uh, real RC4, it takes 256. A key is given, and then S vector will be a series from 0 to 100, 255, and then run that algorithm. T is generated from the key. If I give you, for example, 5621, then you repeat that to fill. No, it's not. Your random number thing is this: if you generate a random number, then your station AP, access pointer in your laptop. So two different random numbers, then they cannot encode and decode for the same. S is serial number from starting from 0 to whatever the capacity permits.
Okay.
And then T uh, is the the same size vector as S, but if key is given short, then you repeat that key. This is what we learned. So once we have S, okay, how many iterations to get this S? We had 8 iterations, right? If you have this. But if you want to the real original calculation for RC4 is 255. So you may get this S by the repetition of this same steps for 256. And the number here, right now we have only 8 numbers in this array or vector. In real example, you need to have 256 numbers of this. Number that we play here, 0 to 7. But in real ones, you have 0 to 255. Big numbers, right? If we extend this to 516, then what happens? A lot complicated algorithm that you can run. But at the same time, the drawback is it takes a lot longer time. But keep in mind, this encryption technology needs to do for real-time streaming data. Data comes in, but generation of the key takes longer than the time data comes in, then it's a lot of mismatches, right? So that is ideal, 256. That is the size for this RC4. So once you have this, then next step. RC4 consists of 2 algorithms. This is the second algorithm. Step 3. At this step, we finally generate K. K. Okay. So this is S. We have while loop. As far as we need K, this loop is running. So initial number for I and j is 0. So let's take a look. The first iteration. Why we need to do the first iteration? How many iterations that we need to do in this case, in this particular example? Plain text is 4 numbers, 4 characters. So we want to encrypt 4 characters so that we can generate first K will be used for first character, second K will be used for second character, third K will be used for third character, and so on and so forth. Right? So this value comes in, then as value comes in, a new K is generated. Okay? So continually. So what happens? So between your laptop and access points, you keep sending some data. An access point should receive it, or your whatever, right? Not only between access points and your laptop. Access point and your laptop, between that 2 players, then only the authentication mechanism part of the authentication data needs to be encrypted. But in this case, if you want to send this to your opponent somewhere who is also a laptop, throughout all the communication lines, wired and wireless, this encrypted data is transmitted. Okay, so keep that in mind. We'll do this. Initially, I and j equals 1. So we reset I and j using the same modular that we so far used. If you have 256, then you need to have a modular 255. 256. Okay, I equals I plus 1 mod 8. Initially, I is 0. So 0 plus 1 is 1. 0 plus 1 is 1. Mod 8, then remainder is 1. J is a little different. So previous J plus previous J is now 0. Plus S of I. I is current I, which is modified I. So I is 1, which is, put it in here. So S of 1 is, so 0, 1. So there is a 3. So 0 plus 3, which is a 3. 3 mod 8 is a 3. So we have I and J, 1 and 3. Once you have I and J, then we swap. Swapping technique remains the same, right? So S1 and S3 are swapped. S1 and S3. Oh, S3 here. S1, S3. This is the index, right? So 2473, 2473, 6015. So that is the current S. Now, tricky, right? Now you need to obtain T. T can be calculated from another modular, but SI and SJ. Once you swap this, I and J never changes. Still, I mean, as far as in the one iteration, still remains the same. But you, after you swapped, then you need to take SI. SI means S1. S1 is this, right? And J is a 3, so 0, 1, 2, 3. That is a 3, right? So 4 and 3, 4 plus 3 is a 7. 7 mod 8 equals 7. So T, yeah, new, here new S. So T is calculated. Now this T is, again, this is an index to obtain K. 7, S of 7. After you calculate this, T is, when T is calculated, then that T is fed into this S vector as an index. So S of 7 here, this is the current S. So S of 7 is the last one, right? 5. So 5. This is the first key. Let's say this is the first data comes in. This is the first key, right? So what we need to do is we need to do K exclusive of P. So K is a number 5, and number 5. if you change this to binary code, then that is a 0, 1, 0, 1, right? So 1, 0, 1. Number 1 is 0, 0, 1. So this and this together, we need to do exclusive OR. In symbol, we make this, right? This is exclusive OR. 5 and 1 together, exclusive ORed. Two operands are exclusive ORed. Exclusive ORed. Which means bit by bit, right? 1 and 0 means 1 exclusive 0 means 1. Second bit 0 and 0 means 0. Third bit 1 and 1, that is a 0. So 1, 0, 0 is the outcome of this exclusive OR. 1, 0, 1, 0, 0 means in decimal that is number 4. So what does that mean? Binary, yeah. That way we can do bitwise operation. So number 5 is rewritten in binary 1, 0, 1. Number 1 is rewritten in binary 0, 0, 1, and they are going to do exclusive OR. Correct. So having this 5, you can encrypt the text 1, which is 4. This is a cipher. And for the second one, you have to repeat this for the new key. You are not going to use this again. One time used, then that's removed. So somebody break in, still, okay, I used it. You take it. New, yeah, one more loop. Damn. This is second. And this is a third. So second. This is second. I did the second, and I want you to do the third and fourth. Why? Because we have a four data here.
Can you do two again? Because I'm still lost. No, we can say two. Did you say that? No, he said I did one with you.
I didn't do yet.
No, I'm two. Oh.
I like you are fully motivated. You cannot wait. Okay. So for this second iteration, we need to bring this 2473 6014. 2473 6015. This is a new S, right? And then yeah, it's new I. What is I? I is 1 and J is 3. In the previous slide. Remember that? This is I and this is 3 obtained here in this step. So now it's not anymore this, but I equals 1, J equals 3. So we need to calculate I. New I will be computed by old I plus 1. Old I is 1, right? So 1 plus 1 is 2. So 2 mod 8 equals 2. J is a little tricky. Old J is 3. So 3 plus S I. I is this I. What is that? 2. So J is 3, S of 2, which is this, S of 2 is 0, 1, 2. This is 2. Index 2 points to the value 7. Ah, this is wrong. So 3 plus 7, which is 10. So 10 mod 7 is 2. 10 mod 8. What is it? Right, in this case, we don't do anything. 2. So 2, 4, 7, 5. It's my mistake. That is the reason that we need to do step 2. Stay the same. So this is 2. Yeah, bring 2 to 0, 1, 2, 7, right? 7 plus 7 equals 14. 14 mod 8 is 6. David, you are very good. Math. Probably you went to the best elementary school. So t equals 6. So this is not 4 but 6. S of 6 is what? 0, 1 is 1, right? So this should be 1. So everything is different. So 1 is 1 exclusive or 2. So 1 means 0, 0, 1. 2 means 0, 1, 0, right? So we do exclusive or. Then 0, 1, 1, which is 3. This is exactly the same. 1 plus 2 is 3. So this one is encoded by 4. This one is encoded by 3. But this 2 is not necessarily 3. It's something else. Although the plain text remains the same, they're all the same 2, 2, 2. But because we have a different key, K. So it's not necessarily the same. Right. It's not 3. It's not the same cycle. So what you need to do? Third iteration. Okay, Jessica, now you try to do third iteration. You need to stick to this while you are. Which one? See, you didn't come last week. Exclusive over. We did the preliminaries. What exclusive or can do is, if the two numbers are the same, then returns 0. If they are different, returns 1. Bit by bit. Look at this bit. 0, 0, they are the same, returns 1. 0 and 1, because they are the different, returns 1. 1 and 0, because they are the different, 1. Who are you? Okay. Yeah, 1, this is 1. This is 2. And this is 3. So I converted these two numbers in binary and compute, and then back to the decimal number. Number 1 in binary is 001. How come it's not
So it's always
Oh.
0, 1.
Always.
You see, other people don't understand the
Actually, this is I don't know. In some high school math was that. And also 120 at Mars 120 CIS 120 covers this numbers, and then many 120 means that is a general education for anyone. Whoever studies the bachelor's degree at Mercy should know this, but it doesn't. It's not necessarily everyone still remember. But somehow in your life you probably learned it. That's good. Then it's very hard if you keep in mind. For example, decimal counting. We already know how do you count. You know when you all the numbering systems that we daily uses is 10 numbers, right? 10 numbers can be written in 10 different numbers starting from 0 to 9, right? We have only 10 numbers. So if we do not have any characters, long time ago, right? Then we use only 10 fingers, right? At most cases, because we have bits, so maybe 20. 20 in our language. Numbers can be represented from 0 to 9 to represent 10 different numbers. Binary means we want to represent 2 numbers. So 0 and 1. 10 numbers, then from 0 to 9. We do not, there's no designated number for 10. There's no designated number to 2, although we say that is a binary number. Why? Because it starts from 0, right? Always. 0 and 1. When it comes to 2, then we need to increase one more digit. Similarly, decimal from 0 to 9. And number after 9 is 10, number 10. But there is no designated symbol for number 10. So what do you need to do? You need to use 2 digits. 1 and 0. 1 and 0, we call it number 10. Similarly, if you represented number 2, then you need to have 1 more digit. Number 2. This is number 2. Number 1 is okay. All proceedings, you can pad 0. For example, if you have 17, then you can say 0000017 or 017. Or there's no padding, so 17. There's all 17. Similarly here. Okay, so do the third step. If we do the third step, and then we'll stop for today. We have only 15 minutes. Third step. You do. I ask you to do. This is the third iteration. I want to take a look at this to see if it is correct. I need to change this. Should be number 2. Okay. This was not right? So 1 and 3. 3. So this is 1. So this is 2. So 3 plus S2. S2 0 1 2 7 7 plus 10. So this is 2. So S2 is swapped with S2, which is the same as this. So never change it. So never changed. So S2 and S2, 14. This is 6. 6 S6 is 1. So 1 exclusive over that is 0 0 1 1. So 1, which is a 3. Okay, revised. Second iteration is this, and third iteration is this. Fourth iteration. So fourth iteration. Fourth iteration, 3 and 5. 5. So 3. That is 4 and 5 and 4 as 4. Okay. So this is a new. This is new. This is new. 0 1 2 3 4 6 11. So it's 3. Huh? Yeah. So 4 and 3. So 0 1 2 3 4 6 and 0. So 6 and 0. And 4 and 3. 6 and 0. So 6. So that is 6. 6 here. 0 1 2 3 4 5 6. There's a 1. So there is a 1, which is 1. So 1. So that is 3. So finally, that's not right. Finally, what do we have? So 4, 4, 3, 2, 3. Yeah, 4, 3, 2, 3. So instead of this, 4, 3, 2, 3. Okay. Any question from this algorithm? Khaled? Yeah. Why not?
Your notes. Your notes.
Huh? With the notes? With my mistake, right?
It's great. So we know. We understand.
Oh, with my pen? Color pen? Yeah, I'll do. All this color? Oh yeah, all the calculations. Okay. Okay. So I'm going to. Okay, one more slide. A few more slides. So WEP. What happens here is that we have initial vector and key. Key usually given 40 bits, and the initial vector 24 bits, altogether 64 bits. And then payload, this is your data, and which has also some integrity check vector, ICV, integrity check vector, usually CRC. So we have 32 bits CRC and then 32 bits of payload, altogether 64 bits. So 64 bits from key and 64 bits for the payload, and applied to RC4 the way that we did, okay, because you have a key and that, then you have a payload and RCV. Once you have this payload and ICV, then this payload and ICV is attached to the header data. So we have a header, IV, initial vector, key numbers. This initial vector is known. This is not encrypted. That is a big problem finally. But anyway, so this all together will shift over the wireless communication. No. There's a payload. Yeah. Right. Yeah, there's the data. Yeah. Once you have here, what is the number? 4323 out of 122, right? Right. And then you have a CRC number. Yeah, one of ICV is a CRC, a cyclic redundancy code, I guess. Here, CRC code. CRC code probably learned from network, right? So by looking at CRC code, finally you may be able to see this payload is securely transmitted. this CRC can check payload itself. I mean, it's a cipher, right? It's encrypted already. But if there is any network error, therefore lose some data, that is checked. Once it is checked and it's complete, transmission is guaranteed, then you can decrypt it. So next we will do some issues of WEP. So why WEP has that problems, therefore it is cracked. Mathematically it is known. This is all the proven. Oh, now WEP, there is that problem, right? See, you can see this guy. I want it to be like this. Therefore, if you change your mind, then you will be the green hacker, not red hacker. So we'll do this next. We'll continue to do this next week. Any question? Okay. Plan for the rest of this semester. I need to confirm you. Next few weeks, we will continue to learn wireless network and security issues. And then we'll take midterm exam, which is required one time for this course. And then the rest, hopefully at least 3 weeks, we will do tech nights. During the tech nights, you need to do the group project. Okay? So I want you to make sure that you are involved in at least one specific group, so that you need to talk with your group members about what to do. Okay? So I'll see you next week.